it says that the sum of currents which are entering the junction is equal to the sum of currents which are leaving the junction. It means current I is reaching the junction and current I1, current I1 plus I minus I1, these are the two currents which are leaving. So if I find out the sum of these, then this equation gets satisfied, means left hand side will become equal to right hand side. It means that whatever currents are reaching there, the same amount of currents they will be going out of the junction. Another example if I take, suppose this point is O, which is known as a junction. At this junction current I1 is going there, I2 is reaching there, like this. And from this point current I3 is going out, current I4 is going out, and current I5 is also going out. Then how can I apply the Kirchhoff first law here? According to this Kirchhoff first law, I can write here I1 plus I2, which is equal to I3 plus I4 plus I5. In other words, if I take the algebraic sum of all the currents at a particular junction, it has to be 0. So the sum of algebraic sum of currents meeting at a junction in an electrical network is always 0. And when you apply this rule here, you have to take those currents which are reaching the junction as positive and those currents which are leaving the junction as negative. Therefore, the name of the first law is the junction law, junction rule you can say. Another name is, it is a law of currents or current rule, because it is dealing with the currents. Whatever current is reaching the junction, the same current is leaving. Therefore, there is no accumulation of charges. So, this law is based upon the law of conservation of charge. The second law. If you want to study the second law, again we have to consider same circuit, same electrical network, but what we do, we will take one closed loop. We call this as loop number 1. So in this electrical network, I have a closed loop. It is also called as mesh. In that closed mesh, A, B, D, A. That means we have started from a point. After following the entire closed loop, we are reaching at the same point. That we start from point A, go towards B, and then to D, and come back to A. Then that is called as a closed loop. For the sake of simplicity, what I did, I have taken the direction of the loop along the direction of current. So current is in clockwise direction. Similarly, in this loop also we can select, here this is the loop number 2. So what is the second law given by the Kirchhoff says? According to this second law of Kirchhoff, which is dealing with the voltages, it says that if you traverse along the direction of current, in the direction of current, you have to take the product of current and resistance as negative, because when the current is flowing from A to B, then point A is at high potential, point B will be at low potential. Already you have studied previously that current flows from high potential terminal to high potential point, or point at a high potential to the low potential. Therefore, in the direction of current there is always a potential drop. So here also in the direction from A to B there is a potential drop. So all the potential drops must be taken as negative if you are traveling along the direction of the current. So minus I1 into P, then we have reached the point B. From point B to point D again we have to travel. In that branch BD, current Ig is flowing. If we consider, if you take that capital G is the resistance of the galvanometer, then the product of current and resistance Ig into G is the potential drop across the galvanometer. Therefore, minus Ig into G, because it is in the direction of current. We have reached the point D. Now, when you go from D to A, the current is coming in the opposite direction. Therefore, the point D is at low potential and point A is at high potential. Since you are going against the direction of current and from low potential to the high potential, as a result of that, we have to take the product of current and resistance as positive because you are going in the direction of increasing potential. Therefore, increasing potentials are taken as a positive. Therefore, here I write plus current is I minus I1 multiplied by R. It must be equal to 0. So, this is what the Kirchhoff's second law says. One more example I can give you. You consider this loop, loop number 3 like this, third loop. You know, so why I have selected this third loop is here one cell of EMF E is also appearing. So, in that case, how to apply the Kirchhoff law you should come to know. Now, for loop number 3, you know, start from point A. So, you are going in the direction of current. Therefore, the product of current I minus I1 multiplied by R, you know, high potential to low, therefore, product is negative. Okay. You have reached the point D and you are moving towards the point C. So, the product of resistance and current we have to take, it is also negative. Okay, no? So, it is I minus I1 plus Ig multiplied by S. You are reached the point C. Now, go to this point and come back to here. So, you get a cell here. So, you are traveling from negative terminal of the cell to the positive terminal of the cell. So, therefore, potential is increasing. So, increasing potential can be always taken as positive. Therefore, plus E, you have reached a point here and from here to here there no resistor is connected. Therefore, nothing we write there. So, ultimately, finally, we get this equation and this is called as the application of Kirchhoff's second law. Since the second law deals with the voltages, so it is called as the voltage law, law of voltages you can say. Since it is dealing with the loops, therefore, it is also called as the loop rule. So, like this, Kirchhoff laws are very much helpful for us in solving the problems, numericals related with this electrical networks. How to apply these rules in details we will study in the next class. Thank you.